All right, workshop students, I got a question here about this flagpole one and with the cable. And let me just give you my, answer about the 4 steps. Step 1, get a good understanding of the problem. Step 2, draw the free body diagram. Step 3, write out the equations. And then step 4, solve those equations. All right, so the first part of this is the object, and to get understanding, here is the flagpole. And what it says here is a flagpole has a mass of 28.8 kilograms. And it extends out a length, let me not put it in the diagram here quite to mess it up yet, but this is 3.86 meters. And extends out diagonally from a building, making an angle of 31.1 degrees from the wall's surface. So this is the 31.1 degrees. Now a horizontal, and that's kind of an important piece here, a horizontal cable with a tension of T sub C connects the top of the flagpole to the wall. Okay, solve for what this tension is. Okay, so there's step 1. I got a flagpole and an angle. It's being supported with this cable, and my job is to find what that tension is. So I'd call that, okay, step number 1. Now, step number 2 is to draw the free body diagram. Now, let me just draw the free body diagram on top of this picture. But the free body diagram is to say all the forces. All right, now my thinking always is take the force of gravity, mg, and everything touching it. Now, let me just start with this gravity one. Notice I put it right in the middle of the flagpole. Because when we go to calculate torques, it wasn't important when we did forces. In fact, the first 8 chapters of this class, we never gave our object size. And because of that, we never even thought about this thing called the center of mass. We never talked about torque. We never talked about rotations. None of that was needed. Now, of course, obviously, all that's a little too simplified because in the real world, our objects have size to them. So clearly, someplace along, and that's where we started in Chapter 9, we need to give our object size to them. And, of course, torque and moment of inertia, and angular momentum, for that matter, all have to do with where things are, not just how big they are. So it's important to then understand that you can take all of the individual pieces that make up the flagpole and think of them all as being pulled by the total mass at its center of mass. And since torque is related to where that force is, we need to mark in our free body diagram where the forces are, not just what direction. So forces, when we just deal with Newton's second law of translation, we just care about their direction. We don't really care where they are on the object. But when we extend this to torques and moments of inertia and angular momentum and all the other rotational quantities, where they are located is very important. So my free body diagram is putting not only the force of gravity mg, but also indicating where it is. So it's at the center of the object, assuming the flagpole is uniform. And again, doesn't explicitly say that, so it would read a little better if it said the flagpole was uniform. Just like the earlier one I did with the cabinet. It would read a little better if we said the cabinet was uniform. So we know for sure that the center of mass is the center of the object, because non-uniform flagpoles, and so a flagpole that kind of tapers would have a center mass lower to the base than up at top, and we would have to figure out where that is in order to solve the problem. So the absence of them giving me any information about doing that makes me conclude that the author really means here uniform. I'm going to put it right at the center. So that's an important step, that the force of gravity is at the center. All right, so there it is again. It's the force of gravity, everything touching it. And so cables, we know, pull in the direction of the cable themselves. Ropes and cables, as you can imagine, I don't really have anything that kind of would be a cable. Maybe my little power cord here might be a good way of saying, but if I, were to strap this onto an object, let's say my hand is the object, there it is, and I strap it on, when you tug on it, it can pull in that direction. But what you can't do is you can't push. You can't what we call compress. And also what you can't do is kind of flip it to the side. It's a flexible. So the good thing about a flexible material like a cable, which is does this one say cable or rope? Or it says cable, but a cable, a rope, a chain, a wire, all of these things are flexible. And so what you know is that the direction of the force is the direction of the cable. Now, why do I emphasize that? I emphasize that because let's say we had something that was rigid. Let me just use this electronic pen as something that's rigid, and I'll take the same object. So let's say this rigid object is now braced onto this object. So I'll just kind of clamp on here. Okay, now, with a rigid connection, I could pull like the cable, but I also can push. So we call this tension and we call this compression. And so an important difference between a cable, a rope, a chain, a wire, is we do not know the direction of the force when we have a rigid object. I'll say it again, for a flexible object can only pull. We call that tension. It cannot compress, and it cannot push sideways. We call that a shear. Now, once I get it tight again, then I can have tension and pull my object. A rigid object, there's a lot more unknown about it. See, if I clamp on, I could either pull the object, okay, so that's tension. I can push the object, that's tension. I could even give it what we call a shear, a sideways nudge. So when I have a rigid object then connected to my object, what direction this rigid one is pulling is not obvious. It doesn't have to be in the direction of the rigid object. See, here's where this is important for this problem. So back in this problem, when I look at everything touching it, I see that up at the top there's a cable touching it, but down at the bottom there is a wall, a rigid wall. So for the cable, it's horizontal. I know it can only be under tension. The force can't go this way and it can't be pushing up. But here at the wall, I have no way of concluding from the physical picture what the direction of the force is. The force could be along the direction of the flagpole. It could be straight out. It could be straight up. In fact, since it's bolted, it could even be pulling inward. You just have no clue about the direction of that force. And so you can begin to see, and this is why I was glad somebody asked this one. This is going to give me a chance to show you two important things about this chapter. This is the first one. And this first one is saying when you have forces on your object, by things making contact, look closely at them. Because if they're flexible objects like cables and ropes and wires and chains, you know they can only pull in the direction of them. And that's very helpful because you know what direction it is. And likewise, gravity, you know, is always down. So forces of gravity and forces from chains and cables are easier than a wall. Well, let me redo the free body diagram. All right, so here is the flagpole. Okay. So I know the force of gravity is down, no question about that. And I know the top is with a flexible object called a cable. So I know it's to the left. But here's the one that I have no idea what direction it is. And because of that, I'm going to do the following. I am going to say that the force down here, which your author calls it the hinge, is made up of a horizontal component of some value, so let's call it F sub x, and also a vertical component, let's call it F sub y. And maybe when the two are combined, so maybe I'll just draw a different color so you don't think I'm drawing yet another force. There's only one force, and so maybe that force is up like that. And so this green is supposed to represent the one force from the wall, and then these red ones are the components of that. But notice I purposely drew this green one so it wasn't necessarily in the direction of the wall or in the direction of the flagpole or horizontal. And so this is how we handle a rigid object. And so the rigid objects are tougher. That's really what I'm getting at. So I'll say it again. You know the direction of gravity. You know the direction of a flexible one. You never know the direction from one that can be made up of a tension, a compression, or a shear. And so you just have to say it has components. And remember, our two principles of static equilibrium are adding up the forces in the x direction, adding them up in the y direction, and doing torques. So it's kind of nice to have them broken down into their x and y components anyway. So it's not just a luxury of breaking them down, although it is a luxury. It is a way of saying that you don't know what that force is. You just know that it's going to have an x and a y component, and then you can work through the math, and then you can even figure out the direction of that and see if it is a direction of the flagpole or something less. In my picture, since the flagpole was 31.1 degrees, I'm kind of showing it here at something less than 31.1 degrees. But I really don't know. It could be bigger. It could even be pulling inward. I doubt it because I can just see that this one's an x component, so I need an x component outward. But anyways, that's the step two. That's that big step two is to draw that free body diagram. So I'll say it again, draw the free body diagram, which means draw all the forces, which means draw the gravitational force, which you know its direction is down, and everything touching it. So we've got a cable, so you know its direction, and then we've got a rigid wall. We don't know the direction, so we write it as our components. So this is the step two. This is the free body diagram. Now let me keep that free body diagram close by and handy, because the key, I think, to these problems is making sure you do a good job with step number 2 in this free body diagram. Because now we're going to go to step 3, which is to write out the equations. So as I write out these equations, I'm going to do something like this. Maybe I will put a little line down the middle and say, all right, one side is to talk about the translational motion of this object, and the other side is to do the rotational motion of this object. Okay, so the translation says this: the sum of the forces have to equal ma, and if we're going to be at static equilibrium, a is 0, and so condition number 1 says all the forces should add up to be 0, and in fact that then can be divided into 2 pieces, because we would have the forces in the x and we would have forces in the y. So that is condition number 1, 2 equations here. And then likewise, over here, when we talk about rotation, the sum of the torque equals I alpha, so that's Newton's second law. And maybe I should say that if we keep it simple and only have forces in the x and y, so I only did x and y, no z's, I will only be allowed then to rotate on a z-axis. So this is really a torque on a z-axis, which gives you an angular rotation on a z-axis. But again, just like we said for translational motion, if we're in equilibrium, we want that acceleration to be 0. And so our second condition of equilibrium is what would be the torques. The torques have to come out to be 0. And by the way, as I was hopefully demonstrating with the cabinet, this may only look like one equation, but the reality is we can have an infinite, really, number of equations here, because when you go to calculate torque, you have to pick a pivot point. And what I tried to emphasize with the cabinet and want to re-emphasize here is you can pick anywhere you want. And so we can have the torques equal to 0 around the bottom, around the top, around the middle, around any other point you want to pick. So really, we could get all kinds of equations from here. Which brings me to my second main point I want you guys to see here. And I say second because I'll go back to my first one. So my first one was, hey, flexible objects, we know the direction of the force. Rigid objects, we do not. And to answer that, we write them in their components, x and y. Now, the second thing I wanted to emphasize here is because we have the ability to pick any point we want, pick an easy one to solve the math. Now, what's an easy one? Well, remember the formula for torque. It's R, F, and then the sine of the angle between them, although it can also be written as R perpendicular F. So maybe a quick review here. If I have something I want to turn, like this bolt, and I grab a wrench, and let's say I'm trying to tighten this wrench, so I grab it right here, and I grab it and I apply a force, say, in that direction. The torque is this RF sine phi, where R is the distance from the pivot, so that would be the center of this bolt, to where the force is, so there would be R. F is how much force you're applying, and phi is this angle between them. And you can actually use either of these because, well, if I call this phi 1 and phi 2, phi 2 is 180 minus phi 1. And so since this is supplemental angle, the sine of phi 1 and the sine of phi 2 are the same. So that's nice to show you. That was not the main thing I wanted you to see, but keep in mind then you can look at whichever one you want. I'm not even going to do that for this problem. I'm not even going to look at that angle. What I'm going to do is trying just to show you that if you draw then an extension and draw perpendicular, whoops, that's not perpendicular, that looks much better, sorry, perpendicular, this right here is actually equal to R sine phi. So if you can find a perpendicular distance, you don't even have to worry about the angle anymore. So that can be useful. So both of these calculations for torque are quite useful. And which one am I going to use here? I'm not sure. But here is my second big thing, and I hope I'm not taking too much time in this video that I lose you, because I'm talking a lot more than just this particular problem. But keep in mind then, the torque would be 0 if R is 0. And so coming back to my free body diagram, if I do a calculation about this point, and I'll say it again, it doesn't have to be that point. It could be the middle or it can be the top. But whatever point you pick, actually it could be somewhere in here. It could be even out here. But wherever you pick, keep in mind that any forces that are at that point would give you 0 torque and would not show up in your equation, making your math a little bit easier. So picking the middle is probably a poor decision. Why? Because it eliminates a force that I know. I know its magnitude, I know its direction, and I eliminate it. That's not making things easier. That's eliminating things I already know. It would be better to eliminate things I don't know. And so by picking either the top or the bottom, if I pick the top, I would eliminate this force in my torque calculations, and thereby only having these two. But the best choice would be to pick this point, because if you pick this point as your pivot, these two go away. And what you have left are these two, which these two, you know their direction, and one of them you know your magnitude, and the only thing you don't know is the magnitude of that one. And so you're going to end up with an equation with only one unknown. And so I'm looking at that going, yes, that's the way to solve this problem. The best way is to say, let's use that to our advantage. Let's use the fact that certain torque calculations give us zero torque when the R is zero. And let's eliminate as much as we can. And so I'm going to pick that point. I think that one is going to make it the easiest. And by the way, I should point out, it's probably the one that most people by default, without much thinking, usually pick, because the problem even says the flagpole is here on a hinge and it can pivot. So I suspect that many, without even thinking, will pick this and get the easy one. But it doesn't always work out that way. So I'm going to emphasize, okay, two really important things about this problem. This problem itself is not too hard to do. But I want to emphasize of why there is a difference. So important number one is things that are flexible, we know their direction. Things that are rigid, we don't. And the second thing is a good choice of your pivot can really make things a lot easier. And I claim that usually the best place is the one that has a couple of forces through it, because both of those will go away. Now, if those are forces you already know, then I wouldn't say that's a good choice. But in this case, I can eliminate two forces from my torque calculation, and the ones I'm eliminating from my equations are the ones I don't know, leaving me with only one unknown. And it's great to have one equation and one unknown instead of a system of equations like three equations and three unknowns. All right, so finally now, after all that talking, I can really get to writing out the equations, the step 3. Okay, so again, hopefully that's some good problem-solving strategies. But also it makes it sound like the problem's really harder than it needs to be. So I'll say it again, 4 steps. Step 1, get a good physical picture of what's going on. Step 2, a free body diagram. And that's where knowing when things, a flexible object and a rigid object, come into play. Also, then, as we get into step 3, writing out the equation, we know that with our two conditions of equilibrium, picking a good pivot point to write out the equations can really make things nice. Watch, so let me write out, and I'll just put my dotted line down the middle again. Let me write out this. Get my free body diagram in here. Let me write out the sum of the torques equaling 0 when I pick this to be the pivot. Now, let me do the torque from this particular force, which is the force of gravity. So I'm going to write it as the distance r. Well, I guess I have a choice to make. Let me come back here. I can use this top one or this bottom one. Now, if I do the bottom one, I got to get the perpendicular distance. So I got to go through a little geometry to get that distance. That's fine. But I think this one might be a little easier doing this top formula, because r, I know, is just half the length. And so I'm going to use that formula. and say, all right, half the length. So 1/2 of the length, which is 3.86 meters. And then the force is mg. So m is 28.8 and g is 9.8. And then the sine of the angle between them. Now, maybe I need to come back to the free body diagram here, and especially up here. And so if I extend this out and I use the vertical line from the wall and the vertical line from gravity, these are parallel lines. And so this angle between them would be the 31.1. These are alternate interior angles from our geometry. So I'm going to write that in my math as the sine of 31.1. So there is the torque from gravity. There's the R, the F, and the sine of the angle. Now, I do need to be a little bit careful with direction, and I'll just kind of do the physical picture here. You can imagine holding it at its pivot and thinking about gravity tugging on it. It'll make it rotate. So maybe here's the flagpole. It's going to make it rotate in a clockwise direction. Now, tradition is to call clockwise negative. I see no reason to change that, so I'll stick to it. So this is a negative torque. So that's the first calculation, the torque from gravity. It is a negative. It is this distance away. It is this much force at this much angle. Okay, now let's do the other torque, and that would be coming from this cable. All right, so it's the distance away. Well, that's the length of the rod. So I'm going to be using this formula again to get the torque. Now, I could also do R perpendicular. That wouldn't be too bad, because I can just kind of draw a line up here and figure out what this perpendicular distance is. That wouldn't be bad. But I'm just going to think in my mind that I think this one might be a little easier, because the distance away is real simple. It's directly given. It's just the length of the rod. So this would be a 3.86 meters, okay? The force is what we're looking for, the T sub C. So coming back to that free body diagram, there it is. There's the force. And then it would be the sine of the angle between them. Now, the angle between them would be this angle in here, keeping in mind that this angle is 31.1. So that would be the complement of it. So this would be 90 minus 31.1. And the direction would be a positive torque. Notice that this is tugging it this way, so it would be twisting it in a positive or a counterclockwise direction. So that's a positive torque, and that has to equal 0. But you can then see this was the real advantage, that I haven't even done the sum of the forces in the x direction or the sum of the forces in the y direction, which we called the first condition of equilibrium. I don't even need to do that to answer this question if I have picked this as the pivot point. So maybe I will come back to those, but I'm not going to need them. Now I can just grab this calculator here, and maybe I'll just check the mode, make sure I'm in degrees. Okay, I am. And getting this first one, this is a 1/2 times 3.86 times 28.8 times 9.8 times the sine of 31.1. So this is a negative 281.4 Newton meters. By the way, it's tempting, but never call that a joule. If you start calling it a joule, you're going to think it's energy. And that's kind of how the default of the physical world is. We just tell students, look, don't ever call that a joule. You call it a joule. Joule is a unit used for energy, and that's misleading. So to keep our thoughts straight is we just really decide never to call a Newton times a meter a joule. And for that matter, it's also best when you're working with energy never to call a joule a Newton times a meter, although that's really what it is, so you can't really say that. But it can be confusing. In fact, let me come back to this torque one. You can see that the force and the distance, being this arm, is different than the energy. If you actually moved it, you would move along this distance. So you would say force and then the component of the force in this distance. So the energy is a different distance. It's the same force, but it's a different distance. And so this torque calculation is not the same as the energy. And that's really easy to get confused. And that's why we always like to say, never call that a joule. Otherwise, you may confuse yourself. Okay, so plus, and then if I put this together, let's see, 90 minus 31.1 is 58.9. Let me take the sine of that and multiply it by the 3.86, and that's actually in units of meter. And so this would be a I'll call it 305 meters, and then TC equals 0. So a meter would cancel off of each of them, and then we're going to be left with TC in units of newtons. So if I take that 281.4 and I divide it by this 3.305, I get a tension of 85.1 newtons. And so I guess technically I'm done. Hopefully I didn't talk too much. Wow, I'm 32 minutes into this. But I feel like I should, just for completeness, also come over here and say, look, if this problem was a little harder, we could say the force in the x direction from here minus TC should equal 0. That would be our forces in the x direction. And the other one would be force in the y minus mg would equal 0. And so if this was a harder problem, we could see that we could actually solve for Fx. Fx would be the same, so 85.1 newtons. And Fy would be equal to the weight, just mg, which 28.8 was the mass, and 9.8 is g, and so that is 282.2 newtons. And so if the problem asked what is the force that this hinge is putting on here, I could then say it would be the force in the x direction squared, force in the y direction squared, Pythagorean theorem. Because remember, that's really what this is. The force from the wall, these are just the x and y components of the force from the wall. And so it might be kind of fun to figure out this question about what is the magnitude of the force that the wall is putting on. And I know that wasn't the problem, but I said a lot of other things that weren't part of the problem. But let me put those in. So what's in my calculator right now is already the y component. And let me square it. Let me add that to, and I'll go up here and then just copy the x component and square it. I'll add those and take the square root. And so if somebody was asking for what I would call the total force that the wall is extending on the flagpole, I would get 294.8 newtons. And we would need to know that number if the question was, is the hinge strong enough? Is the wall, which maybe the wall's made out of wood or concrete, is it strong enough to handle that much that much force. And by the way, we could also, and I'll go back to the grain, answer an earlier one here about what is this angle in here. Because we could go tangent of that angle, and as we look opposite, we would get the x component, and then this would be the y component. So the x component is this 85.1, and the y component is the 282.2. And so, again, just out of a curiosity, extending this problem maybe a little too far, let me take the 85.1 and divide it by the 282.2. Let me take the inverse tangent of that and get an angle of 16.8 degrees. And again, this is my chance of emphasizing to you that the direction of the force from the wall isn't necessarily along the direction of the rod. And if you assume that at the beginning, none of this works out right. You just get it wrong from the very get-go that you assume the direction was the direction of the rod. So I'll say it again. You can go ahead and assume for flexible objects like cables, wire, chains, rope, string, yet they're all in the direction of that cable. They only pull, they never compress. But you have no clue then about a rigid object. I'll say it again. If I, take a rigid object here, back to my rigid object, I clamp on, I can pull, I can push, I can even twist, or some combination thereof. So I don't know what direction it is from start with. And I would have never guessed that it's 16.8 degrees. I kind of got lucky. It looks kind of like in my picture that I kind of guessed somewhere in that ballpark, about, half of the 31. But that was purely a guess. I didn't know. All right, well, I said a lot more beyond this problem. Hopefully that wasn't too much, but hopefully it was also enlightening as you go forward and you get to harder problems, and even as you move forward in your education after you finish this class and you move on to other classes, both with me and then beyond. When you transfer, you'll have a deeper understanding of this material. All right, take care.